Hello, welcome to a new unit on complex numbers. In this unit, we are going to try to define what is the argument of a complex number and the representation of complex numbers in the plane. The minimum requirements are a little more extensive than previously. We are accumulating concepts. They are to know what a complex number is, to operate with complex numbers, modulus of a complex number, and know how to handle the basic trigonometric functions such as sine, cosine, and tangent. We will work mainly in radians, although we will usually say the equivalence in degrees. Well, suppose we want to represent a complex number, a plus bi. What we are going to do is, as a complex number is separated into the real part and the imaginary part, we are going to represent the real part in one of the axes and the imaginary part in another of the axes, in these axes in particular. Notice that we have called the x-axis the real axis and the y-axis the imaginary axis. How would we represent the complex number? Very simple. We take the real part and represent it on the real axis and the imaginary part vertically parallel to the imaginary axis. So this is the complex number a plus bi represented on the plane. Well, what things we need to know? The previous plane is called the complex plane. To each complex number corresponds a point on the plane which we will call an affix. The modulus of a complex number corresponds to the distance from the complex to the origin, or from the affix to the origin. The abscissa axis will be called the real axis, and the ordinate axis will be called the imaginary axis. The purpose of this unit is that every complex forms an angle with respect to the real axis, from the positive part of the real axis to the affix. Well, that's going to be the definition of argument. We'll see it right away. Look at the graphical representation. Here we have the real part, the imaginary part, and the graphical representation of the complex number a plus bi. If you notice, above the hypotenuse, you have the absolute value of z. That is the distance that goes from the origin to the affix a plus bi. And alpha, in green, is the angle that the complex number forms with respect to the real axis. Well, the more strict definition would be, it is the angle formed by the positive semi-axis of the real axis and the vector defined by the origin of coordinates and the affix of z. This is exactly what we have seen in the previous representation. It is usually denoted as argument of z, or in this case, in the presentation, we will also call it alpha. Well, keep in mind that there is not only one argument, there are infinitely many values of the argument of z. Once we have obtained the angle it forms, we can add 2 pi as many times as necessary to obtain the same complex number. Well, the formula to obtain a complex number is the arctangent of b divided by a, where b is the imaginary part of the complex number and a is the real part of the complex number. It is also very important to note which quadrant the z affix is in. Both are very important to calculate, as we will see below. Notice, where does the formula come from? A fairly quick explanation. If we have the graphical representation of the complex number a plus bi, if we look at the situation of alpha, we have that the sine of alpha is the opposite leg, which is b, divided by the hypotenuse, which is the modulus of z. The cosine of alpha is defined as the adjoining side, which would be a, divided by the hypotenuse, which is the modulus of z. Therefore, if we apply the definition of the tangent, which is the sine of alpha divided by the cosine of alpha, we divide b by the modulus of alpha divided by b, divided by the modulus of z, divided by a, divided by modulus of z, and we are left with b divided by a. If we apply arctangent in both parts of the equality or clear alpha, what we have is that alpha, the argument of the z number, is the arctangent of b divided by a. It is very important to know in which quadrant the complex number is located. Here we have a representation of the quadrants. The first quadrant is when the real part and the imaginary part are positive. The second quadrant is when the real part is negative and the imaginary part is positive. The third quadrant is when both the real and imaginary parts are negative. And the fourth quadrant is when the real part is positive, but the imaginary part is negative. If we have a complex number that is in the first quadrant, that is the real part and the imaginary part are positive, its representation is like this. As you can see, the angle alpha is an acute angle and is in the first quadrant. If the complex number is in the second quadrant, that is, the real part is negative, what we get is a representation of this form. You see that the angle is obtuse and comes to meet the affix, which is in the second quadrant. If it is in the third quadrant, we have exactly the same. We measure the angle from the real axis until we come to touch the complex number, which in this case has the real part and the imaginary part negative. We could also have measured the angle in negative, that is, from the real axis down, and say that the angle would be in this case, for example, minus pi quarters or minus 5 pi quarters. This way of measuring it is to try that the angle is always between minus pi and 0. In the fourth quadrant, we have the same thing. If we want to measure the angle, we measure from the real axis and go through the whole angle until we reach the affix, up to the complex number x minus yi there. In this case, the imaginary part is negative. We can also measure the other way around, measure from the real axis down, and give the negative value. In this case, for example, the representation would be minus pi quarters. That would be the negative meter. So far, we have seen the definition of argument of a complex number, and we have tried to represent the complex numbers in the complex plane, so we have called it. Well, in the next units, we will see examples of how to calculate these complex numbers, and so we will have a little bit more tools when it comes to calculating them. So far this unit, thank you.